talk about 6.2 volumes. And the basic idea is the same way. There's two different methods depending on whether you want to take cross-sectionals perpendicular to the x-axis or whether you want to take cross-sectionals that are perpendicular to the y-axis, okay? So the general idea is you have a situation like this, and here's the x-axis right here, this x-axis, and you have points, you have values a and b, and then you have some kind of a, it's a three-dimensional region, okay? But let's kind of put it up here. Let's suppose that we had like some region that does something like that. Okay. Some kind of like the hose or, you know, something, some revolution or something. But it's a solid object, okay? And so the idea is you're integrating from A to B, and there's a typical value of X. Let me just kind of write a typical value here. And if we were to take that typical value and at the plane that is perpendicular to the x-axis, consider the plane that's perpendicular to the x-axis. So the plane kind of cuts up through here. It cuts up through the object. Okay, and if you look at this part of it and you pull it out, then and you let it flat, then maybe it's a circle or something. Okay, I magnified it a little bit while I was at it. And so this right here would be our A of X. Okay, so you're finding an area like that. And if you integrate all such areas from A to B, A of X dx, then you end up with the volume of this object. Okay, likewise over here, the only difference here is that your object might be something like this. It might be like over here from C to D. Okay, that's the only difference. So here in this situation, you're integrating in the y, and then so here a typical value of y would give you this cross section like that. Okay, it kind of looks something like that in terms of y. Okay, so that's the basic idea. Now, in practice, in this section, what we're going to be looking mainly at are solids of revolution, where you take a region and you revolve it about an axis. Okay, so for example, here's our first example, number 1, where we have find the volume V of the solid obtained by rotating the region bounded by these curves about the x-axis. Okay, so y equals the square root of x minus 1. If you square both sides of this equation, then you're going to get this. So you have, and if you solve for x, and it's x equals y squared plus 1. This is a parabola that opens up to the right, and it's actually this one right here. Okay, it's actually this part. It's just, and well, this is the parabola. This is just the upper half of it. So it's also this right here. These ones are out because it's neither of those. These are parabolas that would be like y equals x squared or x minus 1 squared or something like that. Okay, so here that's the first one, and y equals 0 here is the bottom curve, and x equals 4 is this over here. So these are the 3 boundaries of the region. And here, let's see, this is y equals 4. So it should be right here. So that's not it right there. So it's got to be this answer right there, the first one. And that's being revolved about the x-axis. So you're taking this region, and here's the x-axis, and you're revolving that about the x-axis. So what's going to happen is you're actually going to get an object like this. Well, if you look at it from the side, it'll look like this. But if you take a cross section, so that'd be x right there, if you take a cross section, then that's going to look like, it's going to be a circle, or not a circle, a disk. So the thing is that the disk is a circle that's been filled in, is the interior of the circle. Okay, plus the boundary in this case, so closed disk. Okay, so that's going to be a disk when you take that out. And you want to calculate the area of that disk. Okay, now since we're taking cross sections that are perpendicular to the x-axis, I'll just remind you, we're following this model here as opposed to this one. Okay, we're following this model because they're perpendicular to the x-axis. Okay, so now we look for the area. The area of a disk is pi r squared. Now we just have to figure out what r is. R is actually this distance from here to here, which is the square root of x minus 1. Okay, so now in this case, r was just this, but sometimes it's not going to be that. So you have to really look at the graph and try to determine what r is. And a good way is to say, take this value, which is the square root of x minus 1, minus the value at the axis of rotation, which is 0, okay, which is y equals 0. This is y equals the square root of x minus 1, y equals 0. Subtract 0 from this, and you just get this in this case. Okay, so that's our area right there. And so the volume is going to be the integral. In this case, it goes from x values go from 1 to 4, and that's where we have everything going on, not 0, 1 to 4. And we put, of course, with the area in there, which is pi times this squared, which is going to be x minus 1 dx. And now we can go ahead and calculate that integral. Let's see, integral of x is x squared over 2. Integral of 1 is x, and you're evaluating that from 1 to 4. So plug a 4 in, that's going to be 16 over 2 minus 4. Then subtract and plug a 1 in, that's going to be 1/2 minus 1. And when you work that all out, I end up with 9 pi over 2. And working all that out. Okay, so that should work out. Also, with this particular problem, let me just show you this. I'll just show you this one time. So here we have this revolved about the x-axis. Now, Webassign shows you something else. So let me actually go to Webassign really quick. Okay, so here it is in Webassign. It's this problem right here. This is the region that we're looking at. They have these interactive graphs. And if you look at this one right here, this is kind of showing you the region being, that region that we described being revolved around the x-axis. And these are showing different regions being revolved around the x-axis. It's really this one right here. I guess you can interact with it a little bit. You can kind of twist it around and kind of see what's going on. Get a different looks at it from different angles. So I guess that's kind of interesting. And then it shows like a typical cross section right there in the middle, that dark red shaded region right there. Okay, so it's good to look at the interactive graphs. Okay, let's go back to the problems. Okay, let's go to the next one. Number 2. Find the volume of the solid obtained by rotating the region bounded by the curves y equals x cubed, y equals x, x greater than equals 0 about the x-axis. So we're looking at y equals x cubed. Okay, this looks like y equals x cubed right here. This is not, so that's out. This looks like y equals x cubed. This also looks like y equals x cubed right here. And this doesn't. So throw those out. So throw those two get thrown out. And then y equals x would be this straight line right here. Y equals x is there, but it should be the region that's between those two. So it should be this region here. So you can throw that one out. And we'll just go with this one, okay? Okay, now this is being revolved about the x-axis. It's being revolved this way. Okay, so what's going to happen is this line here is going to get revolved down to here, and this line here is going to get revolved out right here. Okay. And in this case, when you take a cross section, you're going to get what the book refers to as a washer. Okay. Kind of think of it as a donut if you're hungry. So this is a washer. That's typically what all calculus textbooks refer to it as. A washer. And so it is going to have an outer radius and an inner radius, and the area is going to be pi times the r squared, the outer radius squared minus the inner radius squared. So you just take, basically what it is you take the area of the whole disk with the radius capital R, and then you subtract the area of the disk of radius little r from it. Okay, and that gives you the area of the washer. Okay, so let's go ahead and set up our integral for the volume. Now you're going from 0 up to 1. These intersect at 1, and you can tell that by setting these equal to each other. It also intersect at 0 and also here at -1, but this is the one that we're interested in. Okay, so if you go from 0 to 1, so integrating from 0 to 1, and we integrate this right here, so pi. The outer radius is x, y equals x. And the inner radius is x cubed, so x minus x cubed. Except I made a mistake here. They're supposed to be squared, so we'll go ahead and square those. Okay, so pi x squared minus x to the 6th. Okay, so integrate x cubed over 3 minus x to the 7th over 7. Integrated from 0 to 1. And that gives you 1/3 minus 1/7 times pi. Or I guess 7 over 21 minus 3 over 21. This is multiplying the numerator and denominator by 7, and then multiplying the numerator and denominator by 3. So we get 4 pi over 21. Okay, great. Now, again, for this problem, Webassign also has a characterization. So we're evolving, what is it, this region here? That's going to be this one here. And this shaded in dark red is a typical cross section, which is a washer. And you can kind of see the trace there. You can kind of see right here the light red. Right here it's we can see it better here. Y equals x here, and then y equals x cubed here. Okay, so let's go back to the exercises. If there's any questions, just let me know, or you can say something, or you can type something in the chat, and I should be able to see it and respond. Okay, so number 3, find the volume V of the solid obtained by rotating the region bounded by the curves y equals 3 sine x, y equals 3 cosine x, between 0 to power of 4, about the line y equals -1. Okay, sketch the region and then sketch the solid and a typical disk or washer. Okay, so here we have the region we want to sketch, or it's going to be one of these. Okay, so y equals 3 sine x. That is going to look something like this, except it's going to go up to 3. Okay, so I look for something that goes up, starts from 0 and goes up, like this right here, or like that. Okay, this one doesn't have anything that does that, and neither does that. So those two are out based on just the first one. Okay, now this one right here, y equals 3 cosine x. That one is going to start up here. Is going to start up here at 3 and come down. Okay, and it's gonna intersect here at pi over 2, but we're only going to pi over 4, so really it's going to be just like it's only going to be just this part here. So that looks like it right here. And so does this, but this doesn't. This doesn't have anything. So it's going to be this one. So this right here is y equals 3. Wait, y equals 3 cosine x. And this down here is y equals 3 sine x. From 0 to pi over 4 is right here. So it's this region. And you're revolving it about this line here, y equals -1, which is down here. So it's being rotated about this axis. Okay, so in reality, if we take this point, this point's going to rotate here, and then this region is going to rotate through here. So let's see, here's -2, 3, 4. Oh wait, wait. Oh, we're on the other graph. Hold on. So that's like -1. -4. Wait, no. -5. Confused. Here's -2. -3, we'll say that's -3, and there's -4. 2, and -5. Okay, so I'm really mixed up here. Let me just like erase all that mistake. Start over. Basically, what's going to happen is starting from here, it's going to go 3 units down to there, and be like that. Okay, so all that's going to rotate around here. Okay, so the reflection is going to look like that. Okay, so it's actually going to be some object with a hole in the middle. And if we take a typical cross-section here, if we take a typical cross-section, then that's going to look like, and I mean, I'll have to shrink it, I guess, but that's going to look like a washer. Okay, like that. And the outer radius is going to be from here to there. Okay, so it's going to go from the outer radius is 3 cosine x plus 1. And the inner radius is from here, 3 sine x plus 1. Okay, so we're looking at, so in other words, For the outer radius, we're looking for this distance right here. This distance here. Now from here to here, it's 3 cosine x. But then from here to here, it's another 1. So you have to add a 1 to it. And likewise, for the inner radius, we're looking at this distance. This distance here from 0 up to here is 3 sine x, the height of this curve. And from here to here, it's 1. So that's 3 sine x plus 1. Okay, so that means that the volume is going to be integral, we'll go from 0 up to, okay, where do these intersect? Figure out where they intersect. To figure out where things intersect, you set them equal to each other. Okay, so you have sine x equals cosine x. That happens when x is pi over 4. Okay, so this value here is pi over 4. Okay, so you're going to integrate from 0 to pi over 4. And pi times the outer radius squared. Oh, this is really nasty. Minus the inner radius squared. Dx. Okay, so let's see. This is going to be 9 cosine squared x plus 6 cosine x plus 1. And then we have minus 9 sine squared x minus 6 sine x minus 1. Well, nice. The 1's cancel. Check that out. I'm going to put the dx back on. Okay, so we have, there's a identity from trigonometry that says that cosine 2x is equal to cosine squared x minus sine squared x. So we'll just use that right now. And that means that these two pieces, that and that combine to give us 9 cosine 2x, not cosine squared, but cosine 2x. Okay, then we have plus 6 cosine x minus 6 sine x. Okay. Okay, great. Now we can integrate that one. That's not too bad, I think. Integral of this. So that would be sine. Okay, so if we take the derivative of sine 2x, we get cosine 2x times 2. So if we just divide by 2, we got it. Then this one right here is 6 sine x, because the derivative of sine is cosine. And then here, it's going to be 6 plus 6 cosine x, because the derivative of cosine is negative sine, so it gives us the negative there. And you're going to evaluate that from 0 to pi over 4. Okay, if we put pi over 4 in here, we get sine of 2 times pi over, that's sine of pi over 2, that's 1, so that's 9/2. And then sine of 6, sine of pi over 4. Actually, you know what? I should not be confusing here. Let me do this. Okay, we'll evaluate these things later. Okay, that's the upper limit. Now subtract and put the lower limit in. That's minus also, like 6 sine 0 minus 6 cosine of 0. Okay, this is going to be 9 halves. Sine of, let me do this. So pi over 4 gives you 1 root 2. So sine of pi over 4 equals 1 over root 2. And also cosine of pi over 4 is the same thing, because it's be this over root 2. Okay, so both of these are 1 over root 2. So we have plus 6 over root 2 for this one, and then another 6 over root 2. Okay, this one is 0, sine is 0, 0. That's also 0, sine is 0, 0. And then cosine of 0 is 1, so that's going to be minus 6. Okay, so you get negative. So combining the 9 halves and the negative, this is the same as negative 12 halves, right? So negative 12 halves and 9 halves, that's negative 3 halves. And then these two combined together is going to be 6 root 2. Well, 12 over root 2, but the same. But if you rationalize these out, you can also put 12 over root 2, or it'll be 6 root 2, all times pi. Okay, and that should be the answer right there. And again, this has a version in does this have a version in Webassign? Yeah, this has an interactive graph in Webassign as well. Here's number 3. It's this first one right here. So here you can see that you're revolving this. Wait a minute. Okay, you're revolving this about the axis y equals negative 1. So this is the middle of the axis right here. You can see right there at negative 1, and then at negative 2, this one goes down to negative 2. So this goes down to here, and so that's kind of what it looks like. Okay, great. Any questions about anything? Okay, let's go to the next one, number 4. Find the volume of the v of the solid obtained by rotating the region bounded by the curves y equals 8x cubed, y equals 0, x equals 1, about the line x equals 2. Okay, so y equals 8x cubed, that is going to be that's going to look kind of like y equals x cubed, except it's going to be taller. So we're looking something like this. It would come down to here if we were to continue it to the left. Looks like that. None of these other ones look like anything like that. So based on just that, we can just throw everything out just based on the first one. Okay, because that, like I said, that should look like this. It should just look like x cubed, y equals x cubed. Okay. So this must be y equals 8 x cubed. When x is 1, we're up here at 8. So that's good. And then y equals 0 is here. And x equals 1 is over here. So that's the region right there. And revolving that about the line x equals 2. So here's the line x equals 2. Okay, so we're revolving it this way. So that means we're going to get, when we revolve it, we'll get something over here as well. It will revolve like that. Okay, now if we take cross sections this way, then they're just going to look really weird. It would be like taking an object like this and then just cutting it down this way. So your cross section here would be a kind of a rectangle, okay? It would be rectangle. Here would be like two rectangles, and here would be a rectangle. Okay, and these are really hard to deal with, so let's not go there. So instead, what we're going to do is we're going to use the other option, and that's we're going to integrate along the we're going to integrate on the y. So that one, when we do cross sections, they're going to look like this. Okay, so cross section in y, and that would look like that's going to be a washer. Okay, when we do that way. So we integrate in y, and the area is going to be pi times the outer radius squared minus the inner radius squared. Now, when you do that, you have to have everything in terms of y. So that's the big thing. Here we have y equals 8x cubed. We need to have x equals something. So to do that. Okay, but so we need to convert this by solving for x. Okay, so let's switch sides of the equation, divide by 8. Then we'll take cube roots of both sides. Cube root of 8 is 2. So x equals y to the 1/3 over 2. So that's what we're going to use instead. X equals y to 1/3 over 2. Okay, now, we need to figure out what the outer radius is when we have this object right here. The outer radius is going to be from, let me get another color here. Okay, the outer radius is going to be here. That's the outer radius. Okay, now this distance here from 1 to 2, that's 1. And hold on. Hold on, let's do this. We'll take this distance here is, this is the best way to do it. This distance here is 2. From here to here is 2. Okay? So from there to there is 2. So from here to here is y to the 1/3 over 2. Okay? So that's going to be 2 minus y to the 1/3 over 2. That's what this distance is going to be. Okay, so once again, the whole distance is 2. From here to here is 2. From here to here is y to the 1/3 over 2. So that's what x is. And this is x right here, right? This is x. And x is y to the 1/3 over 2. So that's this distance here. So this distance from there to there, is going to be 2 minus that. Okay, so that's going to be 2 minus y to 1/3 over 2 squared. Okay, now the little r, that's much easier. That's just going to be 1, because from 1 to 2 is just 1. Okay, so that's going to be 1. And 1 squared is just 1. Okay, so there we go. Great. So now let's go ahead and calculate the volume. You're integrating from 0 to 8. From 0 to 8, because that's where all the cross sections are that don't mean anything. When you're taking pi, the inner radius squared, this one right here, we can go ahead and expand that out. Let's see here. This is going to be 4 minus, let's see, multiply this together, you get the 2's cancel, multiplied by 2, that's minus 2y to the 1/3, and then plus y to the 3/3 over 4, and all that minus 1. Okay, so let's go ahead and integrate. Integrating this gives you 4y. Integrating this one gives you, let's see, if we add 1 to 1/3, we get 4/3. That'll do it. So if you take the derivative here, you have a 4/3 coming down. This 2 reduces the 4 to a 2, and then 3 cancels with that 3. So we have this if we differentiate that. Okay, here, the key is, okay, y to the 2/3, add 1 to that, you get 5/3. Okay, so 3, and then a 5 down here, that's going to be a 20. And then minus y. And that's evaluated from 0 to 8. Okay, put an 8 in, and we get 32. 4 times 8 is 32. Okay, put an 8 in here, that's going to be 2 to the 4th, right? So minus 3, 2 to the 4th. Because the cube root, so this 2 right here is cube root, so cube root of 8 is 2, so 2 to the 4th. And then, again, here, this will be 3 times 2 to the 5th over 20. And then this is minus 8. And then plugging zeros in, you get 0. So that's good. Y equals 0 makes every single term 0. So that's good. Yay. I'm glad that it's not integrating from 1 to something, or 2 to whatever. That would be nasty. Okay. So let's see here. 32 minus, let's see, that's going to reduce it to 3 here. 8 times 3 is, 2 to the 3rd is 8 times 3 is 24, so that's minus 24. So we got a minus 8 there. Oh, that's interesting. All of those are going to just cancel. Wow. Yeah. So those are just going to cancel each other out. Okay, and so then that's this term, and this term. Okay, so now we're just left with this one. So 3 times 8 times 4. And that 4 is going to reduce that to a 5. Okay, so 2 to the 5th is 2 to the 3rd, which is 8, and 2 squared, which is 4. And that 4, there's a 4 can factor out of here. So we end up with 3 times 8 is 24. 24 pi over 5. As the answer. Okay, so we come over here to Webassign for this problem. This is the one that's being rotated around. And here, this is going to be the answer again. And you can kind of see, there's the region right here being rotated around. I wish I could pause this. That would be nice. But I can't. And there's a big hole in the middle. And then this is a typical washer right here, this in dark red. Okay, great. So let's look at number 5. Find the volume of the frustum of a pyramid, the portion of a pyramid that remains above after the top part has been cut off by a plane parallel to the base, with square base side B, square top of side A, and height H. Okay, so the vertical height is H. Oh, a lot of variables here. Okay, so these, if you take the cross section at any point, at any height, then you're going to get a square. Okay, now the square on the bottom has side B, and the square on the top has side A. Now, as you go from, so I can make a little chart here describing the situation. So, and then the length of a side. So when the height is 0, the side is B. And when the height is H, the side is A. Okay, so here we're up at A, here we're at B. This goes up linearly. So if we can find an equation that links the height, and we'll let Y be the height, and we'll let the length of a side be X. How about we do that? Okay, so let Y be the height, and or we're gonna just let it be S. It doesn't matter. Let it be S. Okay, and that one doesn't matter as much. Oh, should just erase it. So essentially, what happens is when Y is 0, then S is B, and when Y is H, S is A. And we can calculate what the slope is there. That would be A minus B over H minus 0, or A minus B over H is the slope. So that means that the side is A minus B over H times Y plus B. Okay. So well, let's see here. Let me just show you how this works, and then maybe show you a little bit how I came up with it. When height is, or when Y is 0, this all goes away and you just get B. And when Y is H, you put an H there, then the H is reduced, so you have A minus B plus B, so the minus B and the plus B cancel, you just get A. Okay, so when we plug in 0 for Y, you get B. When you plug in H for Y, you get A. And this is linear, okay? So I essentially got this, it's a little bit confusing because the variables are off, but I got this from Y equals mx plus B, a line, but the problem is that this is an S and this is a Y, okay? So that kind of throws everything off. It's fortunate that the B's are the same. The B is just the y-intercept, the quote y-intercept is B. In this case, it would be the s-intercept, okay? It'd be like that. So I just kind of went off that to get that. Okay, so that means that this right here. You can also think of this as being the equation of the side. Now, if we take a cross-sectional area, if we take a plane and we cut through this with a plane, then the area is going to be S of Y squared. It's the square, so it's going to be all this squared. Okay, so that means that it's going to be all that squared. So that means that the volume, we can get the volume by integrating from 0 to H of A minus B over H Y plus B squared dy. Okay, now the only variable here is the y, so we can integrate it like this, and it's all divided by 3. And what is it? H over A minus B. So that would be the integral right there, and we're evaluating from 0 to H. Okay, because if you take the derivative with respect to y, then this 3 will come down. We'll cancel with that 3. This reduces to 2, which gives you this piece here. Then you'll have an A minus B over H come out, which will reduce with that. Okay, so let's put the H in first. So we have A minus B over A H. Subtract, we'll put the 0 in. This looks really weird. I'm questioning my method here. I don't think that really made things any easier. Okay, all of this, let's see what we got, what canceling we got here. The H's cancel. Oh, good, and the base cancel. So you basically have, oh, this is cubed. So essentially we have A cubed minus B cubed over 3 times H over A minus B. Okay, good. A cubed factors into A minus B times A squared plus AB plus B squared. And the A minus B's cancel. Good, yay. Okay, so this is what the volume is going to be right here. So the answer here would be H times A squared plus AB plus B squared all over 3. Okay, if A equals B, then we have a, so this would come out further. We just have a rectangular solid. And the volume is just going to be HB squared, because A is B. So if you set A equal to B, then this is going to be B squared plus B squared plus B squared all over 3. So that's going to be HB squared. And then if A is 0, then we get a square pyramid. And the volume is going to be, just at A equals 0 here, you're going to get HB squared over 3.